from Roy and Ronnie about the DPIF abstraction. So enjoy.
Hello, everyone. My name is Ronnie. I'm the leading software architect for integrating hardware acceleration in OVS at NVIDIA. In this session, I want to talk about a journey to reach the point that Mao just presented. And also want to show where we're at and what we think is the next evolution to go to the next level of acceleration, because we think that we just scratched the surface of what OVS can do with hardware acceleration. Like this. Okay. So Mao talked about use cases. So I'll do it in short. Customers have 100 gig, 200 gig, 400 gig. So the PPS can be 15 million, 30 million. I don't know what's next. The latency should be very small. And there is new workload for AI, which uses RDMA. So if you don't know what RDMA is, so RDMA means that you can send everything by hardware. There's no CPU involvement. You just tell the hardware, send this data to another host. The hardware takes this data, write it on a packet, send it away. And today, in modern clusters, we need more than that. We need there's the BGP, EVPN, there's like VXLAN, and we need like OVS, and we think OVS is a great tool for that. But if, on the way, packet is going through software, then it won't work. It must be fully hardware accelerated. Okay, skip that. So I want to talk, it's more or less what Mao described, but I want to give you the architecture view and not the R&D view. So the first thing that we did is Linux OVS, which use TC. And on one aspect, it's great because TC works on driver, which is a vendor. So we can do whatever we want underneath. And it has a little bit abstraction layer than RTF flow that I will touch later. But the main problem we have here is that the OVS uses the kernel to execute some of the paths of the packet. For example, in this case, if you have a VXLAN packet, one can send the IP, let's say the same IP is on the VXLAN and on a virtual function. The OVS will send it out to the virtual function. The kernel will see that this is UDP packet with port ID of VXLAN, and we send it back to the OVS as to a tap device, which even it's a pure software device. It's not connected to the hardware. So we need to discover all of that. All these are connected dots that we need to offload. Now, this is difficult and complex, but this is not the part that blocks us, because complex and difficult we can do. The problem that we are facing is that we don't have the overview, or what I call here holistic view of the packet pipeline. We see only like fraction of data, so we cannot really optimize everything. And the other point that software is heavy, connection tracking, we see some results tomorrow, but I can tell you that on hardware connection tracking, we can do 1.5 million CPS, 1.5 million CPS on a single core, which is like very, very far from what we do today with the OVS Docker. The next one is OVS DPDK. And OVS DPDK, on one side, we see the entire pipeline of the packet. Okay, so like the OVS by itself is doing that in software. It's a EMC and SMC, so it attaches packets to real pipeline to do some caching and performance optimization. But we as a hardware acceleration layer, we cannot do that because we have the native offload. We have also here, we see like parts of the pipeline, and we cannot attach it to packet. Speaking about the RTF flow itself, so Mao said most of the things, we realized that it's too low level. One vendor could do in-cap and counter, the other counter and in-cap. This one is a key size of X, this key size of Y. We ended up asking the driver, please give us the items, the RT items, so we can put it. So my understanding at least, that at least here we should have NetDev offload or DPDK, can't remember the name, provider per vendor, because this just we cannot generate a generic API. So this is one aspect. And other aspects I will touch later, which are that when you're hardware accelerating, you should be aware that you're doing that, also on the DPIF level. And I will touch that. And okay. So, next one is OVS P4. There was attempt to do it. There were a few conferences that this was discussed, and it could not merge into the OVS because P4 works entirely differently. Okay, it's acceleration technology, which is very different than I don't know what NVIDIA, for example, is doing. And also here, I didn't deep dive into it to refresh my memory, but you see here also the DPIF, and they want also to touch maybe the off-proto, but it means that the current architecture of OVS is blocking them to have hardware acceleration. Okay. In this section, I'm going to cover challenges that we discovered. This is only like a few examples. We have much more that we discovered that forced us to change the DPIF data pass code. We could not like overcome that with something in the lower level. The DPIF must be aware that this is offloaded. The first example was city. City is a side table. That when you offload, it might be that you see the packet, there is a match, and the action is changing the MAC address, pushing VLAN, and then also the city. Now, if the city itself, the flow doesn't exist, it should go to software for further processing. So now we get in software half-baked packet that we don't know. If we try to match in pure software, this packet will be maybe inconsistent, maybe will drop. We don't know what will happen with that. So we need like to have a new kind of interaction between DPIF and the hardware that tell the DPIF in this packet, we did only X steps on the action, so please continue from there. The famous DPH. So what is DPH? DPH means that you have a hash on 5-tuple, and then you go to one of the buckets to execute the actions. Hardware and software, they have a different hash. Software uses Jenkins, and there's another one. In hardware, each hardware does its own hashing, and it will never be the same, because even if it's the same hashing, hardware might add padding and stuff like that. That it's very hard to overcome. So what happens to customers is that, let's say the first packet is going in software, and let's say a load balancing. It goes to action B, send it to, I don't know, server A. Now there's a TCP connection, and you're doing that. The returning packet is returning to the OVS, and now we offload it. So we have a TCP connection, which has a context in some gateway on the network. And now when it's offloaded, the next packet is going to the hardware. And in the hardware, there's going to be a different hash function. So now it's going to hit a different action in hardware. So the third packet will go to a different server. And this breaks the TCP, it won't work. And in order to overcome that, the DPIF must know that this is hardware accelerating flow, and it must give the hardware, here's the 5-tuple or what you need. Please give me the hash that the hardware will give for this packet, and only then choose the right action, or else things will break. We try to do something. Try to do something in NetDev on TC that the TC will ask the hardware, but there was a big objection on that, so we let it go. But this is how we work in OVS Docker. We ask the hardware what is the hash, and even between hardwares, we have a different hash. Next one is meter. If we have meter have one state. Either it's in the hardware or in the software. You cannot like have two, because some of the packets are still going through the software. So you need to consult with the same meter or get tokens from the same meter. So the way that we had three ways to overcome that. First, we ignore it, and this is not always good. The second one is we try to send the packet to the hardware to do only the meter. And the next, on next hardware, we plan to have like, we're going to send a wookie or send a message to the hardware, please give me tokens. And the hardware will reduce the tokens and will give me a color, red, blue, red, yellow, or green. It depends on the meter. But this like puts another level of difficulties, because what I do at the time that I'm asking the hardware, it might take 1 microsecond. So I'm just halting the CPU and waiting. We have async API. So we prefer to put these packets aside and go to process the next one. But then we might get out of order. So we need, in order to solve this in an efficient way, and we want the maximum performance of the hardware, we need to do like DPIF surgery in order to tackle all those problems, which might be also different between vendors. I don't know how the vendors handle meters. Connection tracking. So what we have today in connection tracking is that we are going, even with the obvious Docker that we show, and we show performance tomorrow, we are going through the entire software stack of the OVS. And then in the end, we have another layer that is offloading. So we compete, instead of doing it faster, we might do it slower. Okay, so we need to like a way to shorten this distance. And if we speak about NVIDIA, so we have a very efficient connection tracking in Dockerflow that can handle millions of connections per second. And we also can tell you, you can avoid the entire hashing. Okay, we can tell you, okay, this flow is index 7. You don't need to parse the packet. You don't need to hash the packet. You don't need to get a lock on a bucket. You don't need to go through linked list. You can just get the slot in the memory where this data can be found. And when hopefully we will move to this model, which means that we use the software only for exception packets that we cannot handle today, we believe we're going to jump very high in the CPS. This maybe connects a little bit to the revalidation. When a flow or mega flow is in hardware, then software doesn't, counters are not like advancing. Okay, they are not relevant. You need to ask the hardware, is this flow is edged out? So we have a way in hardware to edge out flows. So you just need to tell us if there's 10 seconds you don't see a traffic, then okay, let me know. So all this revalidation that is going flow by flow and collecting counters can be improved when using hardware. You can ask one entity in the system, and it will tell you if you need to remove this flow or not. Okay, so all those issues we are solving currently on the DPIF. The last slide on this subject is that we want to have, we also want to have optimizations, okay, like EMC, SMC. We cannot benefit from that. Okay, we don't see the packets, we don't see anything. We just see a narrow view of the rules. And in order to make it much more efficient and do caching algorithms and other stuff that we talk about, we need to be in the DPIF itself, on the data pass. Data pass must be aware that there is hardware acceleration here. And there was a question on the previous session. This doesn't mean that other stuff won't work, because today we take the OVS data pass, we just change it a lot, add a lot of hooks for the hardware, which we think that will deeply change the DPIF, and the community want that, but we still support everything that is supported on software. Okay. So to summarize this section, okay, this is just a bunch of problems. If you can access me or more later, we have a lot more issues that we had to tackle. But our conclusion is that DPIF requires major re-architecture to support existing and basic functionality. and also with different hardware. Okay, we are not sure that what we did going to be the same for other hardware. Actually, we are sure it is not. Okay. Now I'm going to talk about what is the next phase that we want to go. Okay, so now what we covered in OVS Docker is that we cover most of the needed functionality for customers. And in order to do that, we have to do some solutions on the DPIF level. But if we can do in hardware 1.5 million CPS per core, we are very far from that. And we want to get there. And also in PPS perspective, there are a lot of techniques or hardware strategies that we can do in order to make PPS also better. So what our customers are doing, Mao said that, and I'll repeat that. The customers that must use hardware acceleration, they do what we do. They take the OVS aside, and then they change completely the hardware offload solution. And each one of them might do it differently. For example, if I take it to the extreme, and our customers that just going on the first packet through the entire pipeline software, and then just do one flow also in hardware. I know this has drawbacks because if megaflow changes, you're now going to have storm in the data pass, but each customer chooses its own solution. The offload API they use is RTE flow, and now they are transitioning to Docker flow. Okay. So the problem that what we did until today, it's not a problem. Okay, this is what we did. This was the phase one. Also, if we look at on previous hardware and line rate that we should have achieved, it's a different story than what we are trying to do now in the PPS and the latency. And so what we did, we are below the data pass. Okay, we see just like a fraction of the information, and we try to do what we can do the best. On some functionality, we just can do because it means that we need to change the DPIF. For example, in kernel DPIF, we cannot support. But this is not good enough, okay? Because when we have real hardware acceleration, we also present new problems that don't exist on software only. For example, the megaflows, if you have few megaflows in hardware, you now have 30 million packets per second. Now there is open flow update. You need to remove those flows and add them again. This can cause a storm. Okay, like what is usually happening is everything breaks. So each open flow update breaks the entire data pass. Another thing is that sometimes there is a miss. Packet did some of the pass in the hardware, there is a miss, and it waits in the queue. And now, by the time the packet reach the software execution, the entire pipeline is not relevant anymore because something was changed. I know, if I remember correctly, on the off proto, there is like a fix for that, something that is called freeze, something like that. But we need to have same solution for that. So we need to keep the pipeline until, if a packet started in hardware, the same pipeline that existed on the nanosecond the packet arrived should be the same until it leaves the OVS, or else there is missed functionality. Okay, synchronization between hardware and software, which is hard and look very different between vendors. Also, there's a lot of differences in hardware that we know about. Like, are you working in synchronized mode? You're sending, you configure the hardware, you wait, or you're just sending a message and you can process packets meanwhile. Can you block a packet until the rule is in the hardware? There's a lot of features that are very hardware specific. The key size, how much information you can carry to the software. Today, just a cookie, like 32 bits, and we need much more. For example, in OVS Docker, We just put another header in front and send it to software. Okay, so this is like strategies we are planning to have in order to make it much faster. None of them are relevant to software solutions. So we need to, like, since in hardware acceleration, slow pass is handling less packets, we can use those free cycles and do other optimization. We can squeeze flows, we can identify elephant flows, we can do a lot of stuff because we are freeing a cycle from the software. We can complete pipeline in hardware. Okay, so if we have a miss and you go to software and you do something, then maybe the rest of the flows are already in hardware. So you can send it back to hardware to complete the pipeline. There are different strategies that we can do in order to make it better that we don't do today, and we plan to. This slide is too complicated. I decided to put it, but what I wanted to say here, that CT, which is the biggest table and the most intensive CPS, we have so many options to do it in hardware. We even wanted to send packet if it's going to the city. We not want, and we have a miss in the city in hardware. We want to send it to a different hardware core that will handle that. We want to break it completely in order to get to the real CPS that the hardware can do. And this cannot be done without, like in a common API or generic API inside the DPIF. And of course, other vendors might have their own ideas. It's very, very different. Even we have a few topologies. So to summarize my part, leave some time to worry. So today, the DPIF implementation is software-based. Other optimization are software-based. There's nothing there that can focus in on the willing to accelerate. So we cannot benefit for AMC cache, SMC cache, and so on. We have no view for the packets, and we cannot do a lot of things that we can do when we have more control internally. So the DPIF, let's say, is hardware accelerated well. Also, we think that it's not just that, because we want to integrate it deeply into the DPIF, but this will be very different between vendors. And I took you the P4 approach and the Dockerflow approach, which they don't know where we're going to have a common API. Okay, DPIF was already designed to all the different data paths, and we think hardware acceleration is just one of them. We might also need to have, like DPDK and kernel, there's some differences in the DPIF function calls that you put there. We might need to extend that for hardware, but this can be the common layer for all vendors to generate their own. We will reduce the community effort to help with the offload, and that it will put it on the vendors. And what Mao said, I don't know, it was not clear to me, but the OVS Docker is open. Okay, it will be open source. The things that it's not open is just the implementation of OVS, not OVS, Dockerflow layer. Okay, which is just an API. The API itself is open, but the implementation is not open. So each vendor, if he wills, he can implement this layer, and it will work for him as well. They can also look about what we did and get their ideas, and everybody can benefit from that. Also, it will enable a formal and healthy adoption of what we're already doing and our customers are doing. So we want to have one OVS, and we want that everybody will share the same ideas. We want it to be upstream. We want it to be open, but in order to make it really hardware accelerated, this is the point that we want to integrate. Okay, so OVS for NVIDIA is a choice. OVS for NVIDIA is a choice for customers. And this is what we give the customers. We just want to be a formal upstream solution per vendor. Hey,
it's the second.
This is what happens when someone doing a Google Docs and someone on PowerPoint.
Okay, can we start? Okay. This might be a little repetitive, but we want to show. So we talked about Docker as a new DPIF, and we want to suggest also maybe pluggable DPIF, a pluggable interface in OVS to allow vendors to implement their own DPIF and to maintain it by themselves outside the Open vSwitch library. We want to present how straightforward it is to do it today also. Open vSwitch already supports shared compilation with a flag, already exposing a library, lib Open vSwitch. So a DPIF plugin is just a new library to compile against this lib Open vSwitch. So a suggestion, this is a suggestion here. We can have a DPIF plugin structure to have the DPIF class implementation and maybe some initialization calls that could be used. The plugin can be installed in a shared library folder and then either loaded at initial run of Open vSwitch or when a user creates a new bridge. And of course, this is only the DPIF part. So any core changes like OpenFlow changes, matching actions, new DPIF, pluggable DPIF will need to adapt accordingly. So we took here just an example, DPIF native, just to show how the simplicity of it. Today, we can just take all the native DPIF native files, which actually we just create a new libtool definition. We assign all the files to that definition, and basically we already have native as a pluggable DPIF outside of OVS core. At the bottom, I wrote some remarks about DPIF native specifically, that it has some calls that are not part, they are called directly instead of being part of the DPIF itself with callbacks and stuff like that. So it's less, more direct calls. So it's a little problem there, I need to fix stuff, but this is just for an example. So future work that we can do. This will allow each vendor, of course, to implement its own DPIF, maintain its own DPIF. If it's based on DPDK, then there is some issue with DPDK. So OVS is compiled statistically against DPDK. But this is something that, and then DPDK will give error loading another library that also compiles against DPDK, something to fix there. There is the issue with handling schema configuration in OVS. So that part also, from what we noticed, it's a little problematic if the DPIF is compiled as a shared library. Another thing, if there will be outside plugin, of course, there will be need some version control of each interface that OVS exposed that is used by the pluggable DPIF. So the main one is, of course, DPIF class. We'll need some version control, so OVS will not load a mismatch plugin and probably crash there. We sent the RFC with the example, also the interface to load the plugin, and also how we moved native, just an example to be a pluggable DPIF. Thanks.
All right. So I have one question to start the questions. What I've seen in the past is that we currently have two DPIF providers, so kernel and user space, and there is quite some difference between them. So there's a lot of interoperability, no, not really interoperability, but things that are handled different or features that are missing. I'm afraid if we add vendor-specific DPIFs, we might run into more of those corner cases and specific areas. Did you guys give any thought on how to sort of at least try to align to either the kernel or user space implementation of that stuff?
Yeah, so we, of course we try. You probably saw we want to go with the DPDK, the DPIF NetDev. This is we're going to follow. We're going to stick with that. We might need to extend that because our acceleration is a bit different. Even the off-portal layer could benefit for that, and let's say in the revalidation issues that can be more efficient there. But yes, we're going to want to stick with that and not change this API as much as we can.
Thanks. Any more questions?
Yeah, so one thing that we haven't really been considering previously, we have some documentation and some handling for it, is ABI compatibility between releases. We don't really have any kind of policy for that, and I kind of think introducing something like this, we would need some stronger policy, because we would have backports that potentially could be ABI impacting that would break some pluggable interface. You know, we might have something that we use semantically one way, and we basically just say, okay, you should use lib open vSwitch that was compiled with that vSwitch D. But in this case, we may have some vendor with a plugin that is compiled against, like say 330, and now 331 introduced some semantic change that broke that plugin, but in a weird way, or you know what I mean? Mm-hmm. So from that perspective, I think there's some work to do to formalize a policy, and it may require that we use some of those like libc provider thingies where they can basically version control or version a specific API, something like that, so that we always have it, the right version available. Yeah, so you end up with multiple APIs.
I agree. Here's the answer. Yeah, but you get the offload out. You don't need to deal with the offload part.
So I have a question. So we represent the OBN team at Canonical, and we maintain the packages in Debian and Ubuntu. So I see this proposal as a positive, because the situation now is that we have teams internally that make their living on supporting open vSwitch-based solutions. And before you did this, you are essentially shipping a fork of open vSwitch, which makes a contention. You kind of steal our bread, so to speak. So is the intention with this that we can keep our bread and you can keep your bread and we do it together? Is that the intention with this? Can we ship your binary with our packages, essentially? Is my question.
The package is in what level? In the OVM?
Not as in our distribution package, as in Ubuntu package, essentially.
I guess you can, because this is one of the ideas. It's going to be a replacement. It's not going to be, if you work on the top of the DPIF, it should do the same. It's like obvious DPIF replacement. If it's not like that, we should fix it.
Yeah, cool.
Any more questions? All right. Any online questions? All right, then thank our speakers.